then you're able to always find a non-negative scalar curvature fill-in, or also a positive scalar curvature fill-in. However, in this construction, you can possibly have very negative mean curvature. And in general, you can't expect to have both very positive scalar curvature and very positive mean curvature. And there's a theorem of Miao who said that if you start with any manifold sigma, you can always find some very large constant such that you do not admit fill-in with positive scalar curvature and with this very large mean curvature. And then it's natural to the question, if you can, maybe you can find a fill-in with very large positive mean curvature, but what if you make the more modest requirement and say, okay, we just have non-negative mean curvature and non-negative scalar curvature, which is a question Pengzi posed a few years ago. And when you first see this question, you might want to try to use your standard examples you have to, which appear for positive scalar curvature, for instance, like the torus. So if you take here the torus, which often serves as an example which does not work well with positive scalar curvature. So say you have here, say, the free torus, and say a 4, or somewhere else. And then it's actually possible to fill in the torus with positive scalar curvature. For instance, you can just take a solid torus in Euclidean space, and it's going to have then 0 scalar curvature and strictly positive mean curvature. Or there are also story in spheres with have positive scalar curvature inside. So the sort of most obvious example you could try to use is actually not working, and you can always find such a fill-in. So perhaps the question is actually, perhaps it's actually always possible that you can do that. But in a joint work with Simone Cecchini from TextNM and Rudolf Seidler from Potsdam, we show that actually for almost all manifolds, the answer to this question is no. Namely, if you have any manifold, and we need to assume it's spin, and then if you're in certain dimensions, so say everything in dimension 0, 1, 3, or 7, modulo 8, then you can always find a metric such every fill-in you construct with non-negative scalar curvature must be Ricci flat on the one hand side and must have a minimal boundary. So you have like a scalar curvature rigidity result, and you can also adjust it to the question by Pengzi Miao. And you can formulate in such a way that also on all of these manifolds above, you can in particular find a metric possibly a bit different than the one here, such that exists no non-negative scalar curvature fill-in with non-negative mean curvature. So there's sort of like a vast class of manifolds in most dimensions where you don't have these fill-ins. And the simplest example of this manifolds are the Bezier spheres. So of course, if you take the standard sphere with the standard round metric, you can always fill it in by just taking the ball, which has 0 scalar curvature and positive mean curvature. But you can take another metric, and there's this one parameter family of metrics on the sphere called the Bezier matrix, and you can describe them by a parameter. Where one parameter family is, say, the scalar curvature, and once the scalar curvature of this matrix is below -24, then you cannot fill them in with positive scalar curvature and positive mean curvature anymore. All right, so how can we prove this result? So basically there are 2 steps involved. First, you need to find a metric on our manifold sigma such that there exists a harmonic spinner. So harmonic spinner simply means that it solves the Dirac equation, so d psi equal to 0, where this d is the Dirac operator with respect to sigma. And it turns out that on all of these manifolds I mentioned above, so in these certain dimensions, you can always find such a metric such that you find a harmonic spinner. Roughly the idea is you can do the construction explicitly for Bezier spheres, which goes back to Hitchen, and then there's some work by Hitchen and Baer, where you basically take some very small Bezier spheres and glue these Bezier spheres into any other manifolds. And by doing so, you can control the first eigenvalue of the Dirac operator and make it as small as you want. In particular, you can find these harmonic spinners. So now in this picture, so here's our sigma, and say here would be our potential fill-in omega. And now we have the spinner psi here on the boundary, sigma, and then we prove some extension principle that we can actually extend the spinner all the way to omega. So now the spinner will be, let me call this M. So now the spinner will be harmonic not just on sigma, but on the entire fill-in. And then once you have this harmonic spinner, then you can automatically use the classical techniques like this Neurowitz formula. And that's why you get then either this rigidity result, or once you even have a lot more scalar curvature, then you can also get a non-existence result. And note that the existence is basically using some elliptic PDE methods, or more precisely, we use the Freitom alternative. So it's not some topological method like some index theorems, which make use of some topological assumptions. And therefore, we don't have to impose any topological conditions other than the manifold being spin. Maybe let me pause here for a second for some questions before I come to another rigidity result. All right, so let's talk about more about fill-ins, and this time a rigidity result related to the geometry of the fill-ins. So before we only cared if the fill-in exists or not, and the only thing we want of the fill-in is that it has non-negative scalar curvature and non-negative mean curvature at the boundary. But other than that, the fill-in could be pretty arbitrary. What we're now going to do instead is to look at the geometry of the fill-in and look how big this fill-in is. And one way to measure what the fill-in looks like is the so-called hypospherical radius. And the hypospherical radius is given as the supremum of all numbers rho, such that you have map, which is 1 over rho Lipschitz, from your manifold onto the round sphere with non-zero degree. So basically, you just take like your entire manifold and see like how you can wrap it around the sphere. So the bigger the number rho is, the more difficult it is to wrap it around. You can wrap it around an even bigger sphere, basically. And if you just take the round sphere itself, the hypospherical radius is just radius of the sphere itself. And one thing I wanted to point out in this definition is that we're dealing here with a supremum, and in general, this will not be attained. So the manifold realizing the infimum of all these constant numbers rho will no longer be a smooth map, but will in general just be Lipschitz, and that leads to a lot of technical complications. And then regarding these fill-ins, there's this following classical theorem of Gromov. So if you have some surface sigma and some fill-in with non-negative scalar curvature, then you can always estimate the mean curvature at the boundary by the fill-in radius, by the hypospherical radius of sigma. Okay, so basically, you have here the size of the radius sort of controlling the mean curvature, and we have this inequality. And now what we're interested in is the rigidity for scalar curvature. And Gromov conjectured that if you have this inequality, there's actually only one situation when you can have equality, and that's the round sphere. So it's only achieved for the sphere, in which case the fill-in would be the disk. And in the same paper, we showed that this conjecture holds true. So in particular, if you have equality in this above comparison inequality comparing the hyperspherical radius and the mean curvature, then you have to be a round sphere bounding the round disk in Euclidean space. And to prove this, we're using some classical, we basically would like to use some classical scalar mean curvature comparison results, which have like a long history going back to Gromov laws and the rule, Goethe-Semmelmann, Lord Endle, and others. And however, the problematic part about this is that they're usually stated in the smooth setting. And now the map F we have is no longer smooth, but the one realizing the streamer will only be Lipschitz. So we cannot apply these results, unfortunately. However, what we can do instead, we can approximate the smooth map F by some Lipschitz maps, which approximate this optimal hypospherical radius constant. And then we can prove some almost rigidity statement, which is sort of very similar as in the stability results. So suppose you only almost satisfy the conditions of, say, these results by a rule, Goethe-Semmelmann lot, to what extent are you close to a sphere? And then you'd sort of take like a limit of epsilon going to 0. And it turns out that then, you still have to be the sphere bounding the disk. So here we have another scalar curvature rigidity result. And this inequality of Gromov he mentioned above, you can actually also use these kind of results in the context of general relativity. So there are some further applications. And it's also in the same paper. And so if you have now some asymptotically flat manifold, let me draw like here like a picture. So say we have here in the middle something going on. You have maybe some topology which models some black hole. Maybe here's some galaxy. And then when you go towards infinity, you become more and more flat. And then at infinity, basically, if you just take a very large sphere, here let's call this SR, you can take the sphere and integrate certain quantities, and this gives you a well-defined geometric invariant, which is called the mass of the manifold. And one can express that in terms of the certain integral over here. And this integral over here, so here this equation over here, if you're familiar with Witten's proof of the positive mass theorem, it actually looks incredibly similar. Basically, it's almost the same. However, there's one interesting fact by using these so-called twisted spinor bundles that actually in our existence theory, we no longer need to assume non-negative scalar curvature. So that means that the mass is equal to the integral of scalar curvature, not just when the scalar curvature is already non-negative, but say if the scalar curvature is negative in some parts, you still have that the mass is the integral of the scalar curvature. So that still holds true in the setting as well. So this is sort of like another application of these comparison results by basically just taking some spheres in the asymptotic end of like some very large radius, and then you find a spinor on the interior and in some certain twisted spinor bundle, and then you exactly get this formula over here. All right, are there any questions at this point? to any of the first two rigidity results.
Can the assumption of a asymptotically Schwarzschild be removed?
That's an excellent question. So, like you pointed out, we need to assume that we are asymptotically Schwarzschild, which basically means that near infinity you have to be quite spherically symmetric, like which is quite a bit stronger at infinity than, say, in Witten's proof. However, so basically the advantages of using these twisted spinners and this sort of approach is that you don't need to use this non-negative scalar curvature, but on the other hand side, you have very little control at the spinner at infinity. So we also were not able to take a limit of the spinner as r goes towards infinity. And to compensate this bad behavior of the spinner, we needed to impose some other conditions, in this case on the ambient on the manifold, to make sure that we still obtain the mass at infinity rather than something else. Or for instance, previously this polyhedron comparison results were mentioned. And for instance, in the work of Brendle, where then the matching angle hypothesis is also used, one of the reasons for this is also that here these spinners in general can be quite badly behaved at the boundary, like this psi r squared, which you would like to go to 1, is very unclear if that's the case. Are there any other questions? All right, so then let me move on to my third scalar curvature rigidity result. And this time it's in the context of general relativity, which we already stumbled upon on this very last application. And before I come to this general relativity rigidity result, I first want to make some motivation coming from special relativity. Say here you have some object. Say it has some certain energy. So think of this object, it could be an atom, it could be a planet, it could be a spaceship. And now say it's moving in this direction with a certain velocity v. So it's just this very typical physics problem. And then in special relativity, one of the standard formula tells us if you take the energy, multiply it with the velocity, that's going to be equal to the momentum of that object. And then the main assumption one uses in special relativity is that nothing moves faster than the speed of light. So the speed of this object is in particular less equal than the speed of light, which I call c. And since we are mathematicians and not physicists, the speed of light is going to be equal to 1. And from this simple assumption and the above formula, we can immediately draw the following conclusion. So first, we have that the energy is greater or equal than momentum. That simply follows by just taking the absolute value on both sides of the above equation and using that v is less or equal than 1. And we can also now analyze the case of equality. So what happens if v is equal to norm p and say they're not vanishing? Then the only way this can be the case is if the length of v is equal to 1. But what does it mean if v is equal to 1? That means we have radiation. We have this object that's traveling at the speed of light. So the typical example would be in this case, for instance, it's a photon, for instance, or like possibly a gluon or graviton. And the question is if this type of rigidity result also holds in general relativity instead of special relativity. Of course, to understand what we really mean by that, we first need to understand what is, in this context, energy, momentum, and what does it mean that nothing moves faster than the speed of light? How does this assumption come in? And also we need to know what are the underlying objects we even study in the first place. What are these? Here in this case, they're like particles or planets, but what is the correct notion in general relativity? And that brings us to the notion of initial data sets. So basically an initial data set is just what I've already drawn to you on another slide a little bit back. So you have again something which is asymptotically flat. Then in the middle you have something interesting going on. Maybe here you have one black hole. Maybe you have a gravity well. Maybe here you have a small black hole. And then the key point is once you go to infinity, you have here that the metric is going to the Euclidean metric. But now what we have additionally is the symmetric 2 tensor K. This is modeling like the second fundamental form if you would be embedded in a space-time. And you also want that the K is then going to 0. And all of this, how exactly G is going to the flat metric and K is going to 0, this needs to happen at a certain specified rate. For that's not going to be that important for us, but just at some rate, it should go to the flat metric. And then one can associate to this initial data set also the so-called energy density and momentum density. So basically, they are both cases given by some expressions depending on K and G. But sort of the key, and then we say we satisfy the dominant energy condition if mu squared equal norm J. And now one interesting thing is if you now assume that K is equal to 0. So if K is vanishing, then this term is not here, this term is not here, and these two terms aren't here. So therefore we simply get in the setting that scalar curvature is non-negative. So basically this was titled like scalar curvature rigidity, but in the end this last part will be about this dominant energy condition rigidity. But as you see from this observation, this is like a natural generalization of the concept of non-negative scalar curvature. And these conditions are also very natural. So if you have a space-time, so let me draw like here like a very schematic picture. If you have here some space-time which is Lorentzian and say n+1 dimensional, and then inside here you have your mgk, which is now n-dimensional, and is lying sort of inside the space-time with here say the normal vector n. And then the space-time satisfies the Einstein equations, and that, which relates then the stress energy tensor to the Einstein tensor. And then you apply the Gauss and Kodazzi equations. And then by placing some very natural conditions on the stress energy tensor, you then get via the Gauss-Kodazzi equations exactly the dominant energy condition. And sort of in comparison to what we had in special relativity before, this dominant energy condition is sort of what is like our analog for nothing moving faster than the speed of light. Or more precisely, it would be that you don't observe anything traveling faster than the speed of light. So that's great. We've already generalized the first part of special relativity, general relativity, but now we need to talk about energy, momentum, and mass. And if you look in Newton's physics, that was very easy. If you want to find out what is the mass of some region omega, you just integrate the mass density over that region. However, that's very beautiful, but it doesn't work in general relativity. The reason is that there's no good notion of what mass density is. For instance, for the Schwarzschild manifold, which has a lot of mass, the scalar curvature is actually 0. So here the formula can clearly not hold. And there are sort of now two directions what one can do to circumvent these difficulties. So there's one question about how to sort of define mass of like just locally of an object. And there are many different definitions. I've listed a few of these on the slide. However, it turns out that all of them have some very nice properties. They also have a few downsides as well. So there's not like one perfect definition which is doing exactly what you want. However, there's another option. And this is by looking at the mass only of the entire asymptotically flat region. So again, we are in the setting as before. We have here something going on in the middle. And then it turns out this is it's a perfect definition that you just take some very large spheres at infinity and that the radius go to get bigger and bigger. And then you evaluate certain integrals. And then it gives you a good notion of energy and momentum. The definitions look a little bit, they don't look very pleasant at first and look coordinate dependent, but it turns out this is a well-defined geometric invariant and has exactly all the properties you would want to have of a mass. The only thing is only downside is you only have to measure the mass of the entire space-time. So it doesn't tell you, say in this case, what is the mass of the black hole or what is the mass of this galaxy over here. It just tells you what is the mass of all of these objects together. And the nice thing is then we also have positive mass inequality, namely if you have one of these initial data sets, and then you make this assumption that the dominant energy condition is satisfied. So this was just our analog of non-negative scalar curvature, that then you have that the energy is greater equal than the momentum. And in particular, you have no negative mass. So mass is simply the square root of E squared minus P squared. So just the Lorentzian length of the energy momentum vector. And this result, this has been first proven by the Shen-Yao via the Zhang equation and by Witten using spinors, both around the same time. And since then, there have also been a couple of other proofs as well, which have happened a bit more recently. But the talk is titled Scalar Curvature Rigidity. So we're not just interested in this inequality, but what we want to understand what happened, what if E is equal to P? So what are the spacetimes? And the result is the following. So you're exactly in the same setting as before, but now you assume that E is equal to P, not equal to 0. And then the claim is that you are a gravitational wave. So more precisely, you isometrically embed into a so-called PP wave spacetime with second fundamental form K. I'm going in a second in detail over what these PP wave spacetimes are and how they model gravitational waves. But first, let me point out that as in special relativity, vanishing mass implies radiation. So for special relativity, you move at the speed of light. In this case, we have that you are a gravitational wave. Then this is stated for asymptotically flat initial data sets. But there's also a similar result in the hyperbolic setting from last year. And then the above result was first proven in this spin setting. So if M is a spin manifold together with Yu Zhang. And then there's an upcoming work with Lanzhou and Huang where we also can cover the non-spin case of this theorem. All right, so what are PP waves? But first, let me also talk a bit, briefly mention a bit more of the history before discussing these gravitational waves. So there are actually many situations. So here note above that here we had E equal P being non-zero. But now when there are actually certain conditions which enforce the energy and therefore also the momentum to be 0, which have been established previously. It also has like a long history of like many results, which are listed here. And interestingly, it turns out that if you apply certain additional condition on your initial data set, say in low dimensions, or by putting more strong decay assumptions, then you already have to be then you already have to have 0 energy and momentum, and you have to be in the Minkowski spacetime. So to conclude, if you put in some extra conditions, you actually rule out gravitational waves. So if any of these 5 things I've listed here are satisfied, then you don't have any gravitational wave examples. Okay, so what is a PP wave spacetime? So a PP wave. So first of all, the 2P stand first of all for plane-fronted. So it's a plane-fronted wave, and then with parallel propagation or parallel rays. So topologically, this is simply Euclidean space, but instead of the Minkowski metric, you have the following metric. So metric G is 2du dt plus f du squared plus the flat metric on r minus 1. And here f is a function which does not depend on t, but it depends on all the other variables. And what we want is that if we fix a number u, so once we fix a u, it's only a function r minus 1, then we want it to be superharmonic on r minus 1. So in other words, we just want to have that Laplace r minus 1 f is less or equal than 0 for all u in R. And this is basically the simplest model of a gravitational wave, which is also often used by physicists for their models, and actually have a long history. So they go back to some work of Brinkmann from 1925. So they're now exactly 100 years old. Brinkmann originally approached them from the math side. So the mathematicians won again against the physicists. But the physicists realized that they're very important for the gravitational waves. They also have another cool feature coming from physics, namely they appeared so-called Penrose limits. So a Penrose limit has a pretty cool description in Penrose's original work. They said that basically, if you think yourself as being in a spaceship, and the spaceship is going faster and faster till it almost approaches the speed of light. And then if you sit in the spaceship and you look outside the window, then you see a PP wave spacetime. So by doing this blow-up process, you're always going to see PP wave. So more precisely, you blow up along a null geodesic, and then this is what you get. Of course, if you blow up around a single point, then you just get Minkowski space. And then geometrically, these PP waves also have many cool properties. And one of them I want to mention is that they carry parallel spinors. So parallel spin is just a spinor which satisfies nabla I psi equal to 0. I guess it's the ambient connection. So they have like many cool and useful properties. All right, let's also mention a few examples of PP waves. So as you see in this definition, the only thing which is non-trivial about them is this function f. So basically, once you choose a function f, which satisfies the superharmonicity property, then you get a PP wave. So there are a lot of different ones of them. And the simplest case, when you simply choose f equal to 1, then you get a Minkowski spacetime. Even more generally, if f is just depending on u, you can still reparameterize the metric to see that it's actually, again, Minkowski space. Then another example, and that's by Huang and Li, is that if you take f as 1 plus some cutoff function eta times the superharmonic function kappa, and then it also satisfies these conditions. Of course, eta is only depending on u. So if you fix some constant u, this is just a constant. And then if k is superharmonic, then 1 plus eta times k will also be superharmonic. So it clearly satisfies all the assumptions. And then it turns out that if you choose the t equals 0 slice, then this is going to be asymptotically flat. And in particular, satisfies some an energy condition. And in particular, it has non-zero energy, but 0 mass. So that's like one of the examples which are described in this theorem over here. And it turns also out that if you not just look in the spacetime at the t equals 0 graph, but if you look at some more complicated graphs, then you can actually improve the dimensional threshold from n greater equal to 9 to n greater equal to 5. And it turns out that this is also the optimal dimension. So dimension 3 and 4, you don't have these examples. And also what I should mention is that I think for many people, this example by Huang Li, which was the first time this asymptotically flat example has been found, was very surprising because a lot of people expected that if you have zero mass, you have to be in Minkowski space. But that's, as we see in general relativity, not the case. You can also have these radiation examples. And so this was giving like a counterexample to what many people believe to be true. And the same holds true for other questions as well, as for instance, the Bartnik stationary vacuum conjecture, that if you have a mass minimizer, that you always have to be in vacuum. But as we see here, these PP waves are not vacuum in general. All right, so let's also try to visualize one of these PP waves. So one great way to visualize a PP wave is the following. So think we are just here in Minkowski space, Rn, 1, here on the left-hand side of this picture. And we just take the standard boring Minkowski space metric. And now what we're going to do, we're going to change the metric. Namely, we take here this orange ray and define the metric here a bit more interestingly, say by such a cutoff function as here. And then basically along this ray, also know that it basically extends to the x1 to xn minus 1 directions. Along this ray, you basically have now your gravitational wave traveling. And how exactly does it look like if there's a gravitational wave traveling? One way to do this is just say if you take here any observer moving here along this red line forward in time. And now say you're like this observer over here and you're having in your hand a red square, like I've drawn here. So say we are here in this situation for t equals 0. And then you're just going forward in time, but then at t equal to 1, this gravitational wave is passing through you. And what this gravitational wave does is that it takes the square and it stretches it in the xn direction. So in the direction of the gravitational wave. So this becomes stretched in the xn direction. And therefore you're gonna have then this picture. But then after the gravitational wave goes through, everything contracts again to the xn direction as well. And you're gonna be back to the original picture. So basically you first get stretched and then you contract again. And this is sort of what this gravitational waves are doing. However, if this happens like in real life, if right now a gravitational wave is passing through you, you would actually not realize that because not just that red square is stretching like that, but everything else too, including the room around you and you yourself, you would also stretch in the same way. So it's not so straightforward to actually detect them, but there have been, like with LIGO and maybe upcoming LISA, there have been some practical ways how to find them. All right, so now in the last few minutes, let me talk a little bit about the proof. So I mentioned in this theorem, there are two different proofs. One using Lagrange multipliers in this upcoming paper with Lan, and one using spinors. And I want to talk a bit about the spinorial proof in the remaining time. And there's sort of a couple of steps. So first, as setup, we have a spin manifold, so we also have a spinor bundle. And then you can double the spinor bundle to get a so-called space-time spinor bundle. And the main thing is that you get a Clifford action by Minkowski space. So on the one hand side, if you apply like the time-like vector E0, that switches the components. And so that, and for if you take a spatial vector EI, then you apply Clifford multiplication as usual on the first component, and in the second component, you get an additional minus sign. And then you also have like a few nice identities which are listed below. And now if you go then to Witten's integral formula, here, so basically this formula I've written down for you below. And basically you get the energy and the momentum at infinity, and this is equal to a certain negative integral. Note in particular that this is greater equal than 0 if mu is greater equal than J, so if the dominant energy condition is satisfied. And now basically our goal is to make this term over here equal to 0, because if this is equal to 0, it'll follow that this term is equal to 0, and we have a certain overdetermined equation for the gradient of psi, and that will be very powerful. But now there's a very basic observation. So now if you try to make this term 0, and you can actually choose psi infinity, the spinner, your asymptotic spinner, to be some arbitrary psi 1, and then you just have to choose the second component appropriately. But the key thing is that psi 1 is chosen arbitrarily. And then it turns out that the left-hand side of the Witten integral formula is always going to be equal to 0. So I've given you here the computation. You see, it's just 2 lines and quite elementary. But that means that you have a spinner solving this equation, not just for a single spinner, but you actually have a whole family of linearly independent spinners all satisfying the same equation. And it's going to be quite useful later on to have these many spinners at your disposal. Okay. And now what is the second step? So next we take a spatial harmonic function, which also appeared in one of the proofs for the positive mass theorem from before. So a spatial harmonic function simply satisfies Laplace u equal to minus trace k times norm gradient u. And so if this is our initial data set, let me draw it this time like this. So this is our mgk. And then if you have such a function on there, you get a foliation naturally by level sets. So this is going to be a level set sigma t, where the function u equal to t. And now the idea is that we want these level sets to be flat, because they're going to be the planes of our PP wave, of our planar wave. So what the goal should be is that that the sigma t are flat. And once we can show that the sigma t are flat, we are in business. Then we can construct the whole PP wave, the whole gravitational wave. And to do that, we can use the spinners again. Just one observation before I do the spinorial, go over the spinorial proof, is that we could also just use the Bochner formula for our spatial harmonic function. But that actually only gives that the scalar curvature has to vanish off the level sets, which if you're dimension 3 and your level sets are dimension 2, this is good enough. Then scalar flatness already gives you flatness, but in higher dimensions, the Bochner formula only gives you scalar flatness and not more. Okay, so now let's go back to the spinorial approach. So we have here a spinner satisfying this equation, which we get from Witten's formula. And then we construct a new spinner by the spatial harmonic function and the first component of the spinner. And that's another very direct and short computation. It turns out that the gradient with respect to sigma of that spinner is 0. That means that the spinner is parallel. And whenever you have a parallel spinner, that means your surface has to be flat, Ricci flat. So we already got from Riemann flat to Ricci flat. But now comes the last ingredient. Namely, we have a lot of flexibility for choosing the spinner at infinity. So this choice of psi 1 infinity is arbitrary, but it also means that the choice of our spinner here, which is parallel, is also arbitrary. And you can find a lot of different of these parallel spinners. And when you have a lot of different parallel spinners which are linearly independent, then you immediately obtain that Riemann curvature has to vanish. And therefore you have, as in this picture above, you have here this foliation of your manifold by flat level sets. And each of these sigmas is Riemann flat. And that's actually quite surprising. So even if you think of Minkowski space, which is much simpler than a general PP wave spacetime, that any initial data set of Minkowski space is foliated by flat hypersurfaces, which I think is when you hear it for the first time might appear a bit surprising. And that's sort of like no, that's the main geometric part of our argument. And then let me just briefly iterate what remains to be done. So basically, we have now our m-dimensional manifold, but we now need to construct an n plus one dimensional manifold, which is called a killing development, and the metric is given by this form. And now we have to show that this killing development is actually a PP wave spacetime. And for that, we need to find good coordinates and also then find these parts of the PP wave, namely there are two things we need to do. So we need to find the f of the PP wave. That's the one thing to define the spacetime. But then there's something else. So we also need to find the graph function. Because the MGK is, of course, not just embedding in some standard way. It could be a very complicated graph. And then you can also, and then in the end, you can also analyze the regularity of the graph function. And it also tells you some dimensional thresholds when you have these PP waves and when you don't have them. All right, I think I'll end it here. Thanks very much for your attention and look forward to some more questions. Thank you.
Well, thank you very much, Sven, for a wonderful talk. Are there any questions from the audience for our speaker? Oh, so actually I have one, which you talk about the foliations, right, in the settings of initial data sets. And then in the very beginning, you talk about fill-ins, which does it, the rigidity, does it give you a foliation as well in that setting?
When you have a fill-in, on general, in this type of rigidity, I mean, they're like in the second one, you're gonna be in the rigidity case only a sphere which is filled in by a disk. And I guess you can, I mean, it's just a round disk, so I guess you can construct some foliation, say foliated by round spheres of smaller radii. And then in the other question, in this question by Miao, our rigidity result is basically giving that you have, you basically get from the rigidity that you have a parallel spinner, and that gives you that you are Ricci flat. And in general, you would not directly get a foliation of such a Ricci flat spinner. I mean, in some cases, if you have some parallel spinner, you can use the Dirac current to construct a foliation, but it could also be that such a Dirac current is vanishing and doesn't give you anything.
Oh, yeah, okay, thank you. Okay, are there any questions? Okay, if not, let's thank our speaker again. Thanks for a very wonderful talk. So